Hello, everybody. So now we go into section 5.2 to define the definite integral. And that's basically the limit of the Riemann sum as we let the n go to infinity. Remember, n was the number of subintervals in the partition. All right. And then we will actually do some calculations for easy functions in this second section. And then we will figure out how important this concept is. Now, the computations could get involved. All right, it's going to get, some of the computations will get complicated, but the good news is, okay, you don't have to always do this. And in fact, in the next couple of sections, we will learn this one wonderful theorem, it's called the fundamental theorem of calculus, where that's going to eliminate all the necessity for calculating the limit of the Riemann sum. So that's going to be great, right? But until then, we should and we must look at how to add these, rectangular regions by hand. So let's go ahead and do that in section 5.2. All right, make sure you first carefully look at and watch and take notes on section 5.1. Which had to do with the Riemann sums approximating the area under the curve, because I'm going to go straight into the definition of the definite integral right here at the beginning of section 5.2. All right, so what we are about to define is this, the definite integral, which is basically the accumulation of all those values under f, which has to do with the area of the that region, under the function of f between a and b. The definite integral of f over the closed interval ab is, you ready for this? First, the new notation or symbol. It's that anti-differentiation, anti-derivative notation of the symbol, long or elongated s, standing for sum, roughly speaking. It's the integral from a to b, a is in the bottom, b is on the top, of fx dx. And that is the last thing I wrote in section 5.1. That's the limit, and as n approaches infinity, of the sigma as I goes from 1 to n. Remember, I is just an index of f of xi, where xi star belongs to the ith subinterval, and then delta x. Notice here I am assuming back at the beginning that each subinterval is of the same length, so I am not going to use delta xi, which is necessary if you are using non-regular partitions. Okay, I'm going to say if it exists, because sometimes, as you know, some limits don't exist, right? And I should specify what each part means. A is x naught, which is less than xy, which is less than x2, and it goes to xn minus 1, which is less than xn, which happens to be b. And delta n, x is the length of each partition. Again, assuming in this context or in this definition, assuming that the partition is regular. So delta x is the same for every interval, and xi star, well, let's see, the xi star is between xi minus 1 and xi. Okay, so what is that? All this is saying is that xi star is in the ith subinterval, or subinterval number I, okay, or I is the index. What am I saying? You understand what I'm saying? If you didn't, okay, basically it's saying like the x sub 5 star belongs to the fifth subinterval, and so on. And the fifth subinterval is the interval between x sub 4 and x sub 5. All right. So the setting is all the same, right? And if this thing exists, it is called the definite integral. All right. So I should first just make comments about this notation here. All right, so this elongated thing. Now, why did we use this? Because it has to, this has to do, the definite integral has to do with the sum, right? It has to do with the Riemann sum. So it is natural, I think, to use some symbol, a new symbol, representing sum, or the initial letter of the word sum, which is S. What I can't explain to you yet is why we use the same notation or same symbol for anti-differentiation. Okay, but that reason will become clear after you study section 5.3 and 5.4. So wait for a few days. It's a coming attraction. All right, so in this context here, or in this symbol, these are called limits. Okay, so A is called the lower limits, B is called the upper limit, and these are called, I know the word limit is just overused, but here, this limit is different from this limit, which has to do with the epsilon delta, right? So these are just bounds, upper and lower bounds. These are called limits of integration. Again, understand that the word limit is used in a different sense from the this one here, which has to do with what happens to this representative, or this quantity as n approaches infinity. Okay, these are just bounds. This is the integral notation or integral symbol. Okay, now this is the function that you are integrating, or this is the function, the area under which you are looking for. And this is called the integrand. And that just means it's a function being integrated. And this thing here, you learned this as a differential, right? And it is. Again, I can't explain to you yet why this dx is important here. It should make perfect sense if you just write this, right? Because you can say, let's make that be the symbol for the area under the curve of f between A and B, and that would be fine, except this differential here is for a reason, for a good reason. And so we will just not mention this right now, but just remember that you always have to have that differential at the end of the definite integral. Okay, so I think that's all I'm going to say about the notation. Let me just give you some properties of this integral. So if the definite integral, note number one, if the definite integral exists, in other words, if this limit exists as the subintervals get smaller and smaller, then we say f is integrable on or over AB. Okay, that means the integral exists. If, okay, so not if, this definite integral is the area under f if fx is greater than or equal to 0 on this interval. Now, what happens if it's negative at some parts? Okay, so then that's a little tricky thing. We will address that in just a minute. And in fact, maybe I should say that. Remember, this has to do with it's approximated by the Riemann sum, right? And so the Riemann sum looked like this. If you use, if all the delta x values are the same. This, if f is not, okay, if this assumption is dropped, if f of x can be negative at some parts, this could actually be negative. Okay? And in fact, if it's negative everywhere on AB, this will be all of that is negative. And in fact, the entire thing can be negative, right? So the point is, this can be negative if f of x is negative at some point. Okay, it doesn't have to be negative in the entire interval. So just remember that. So the point is, if f can be negative at some parts, this thing may not represent the area under the curve, which is somewhat easy to misunderstand by beginning calculus students. All right. What else can you say? If f is continuous on AB, okay, then f is integrable. So continuity automatically implies or guarantees integrability. Continuity implies integrability. Remember, continuity itself does not guarantee differentiability, right? Because you could have something, a continuous function like this or like this, where maybe there is a point where the derivative does not exist. So continuity does not guarantee differentiability, but continuity does guarantee integrability. But many non-continuous functions are also integral. So again, it doesn't go the other way around. Integrability does not imply continuity. Okay, and in fact, we studied step functions like these. Remember the treadmill example or driving example? That's like, this is very discontinuous. I mean, every time you go from one step to another, it's discontinuous, right? But clearly, you can find the area under the this non-continuous function. So this function is certainly integrable. In fact, every non-step function is integrable. And so it doesn't have to be continuous for the function to be integrable. But if it's continuous, that is more than enough to guarantee integrability. All right. Let's go to look at some examples. So I'm going to do the first real calculation involving the Riemann sum and its limit. All right. I think this is a life-changing example. In fact, I still remember, and I remember, maybe I'll tell you a story about this one. Maybe I should do this first. Okay. But this is a great example. All right. So just keep this in mind. I hope this is going to open your eyes and change the way you look at the world. F of x is x squared between 0 and 1. Okay, what are we talking about? Well, clearly, we're talking about a parabola. Y is equal to x squared, and we're going to limit our attention to between 0 and 1. Okay. Let's first look at the right-hand approximation. And what we will do is we will calculate the Riemann sum using the right-hand approximation, and then we will take the limit as n approaches infinity. And if the limit exists, surprisingly maybe, but it doesn't matter if you use the right-hand approximation or the left-hand approximation or midpoint or anywhere else approximation. The limit will be the same. Okay, so let's go ahead and check this. We zoom into this interval from 0 to 1. Remember, the left endpoint is x0, and and then the last one is x sub n. We'll divide this into n equal subintervals. So what is that? Delta x is going to be 1 over n, because the length of this entire interval is 1, and we are partitioning this into n equal subintervals. Right. So, well, let's go ahead and look at this. So this is, we call this, x1, and this is x2, and this is x3, and so on. Okay. But we know exactly what those values are. x1 is 1 over n. x2 is 2 over n. x3 is 3 over n, right? So xi is just I over n. I hope you can see that, because basically you're just adding 1 over n each time you go to the next one, right? So this is 1 over n, this is 2 over n, this is 3 over n. The last one is n over n, which is 1. Okay, so that's quite a simple kind of a partition. So here, the area can be approximated. Basically, we're doing all of these, okay? And then the right-hand approximation, so this is what we're doing. Okay, A is approximately, remember the Riemann sum, This is the sum from 1 to n of f of, oh yeah, so the first right end approximation, the value for the first, I should say the representative of the first interval is the right endpoint, which is x1, okay, which is 1 over n. And then for the second, well, the representative of the second subinterval is going to be its right endpoint, which is 2 over n, right? So let's go ahead and write this. This is just a definition, right? But in this case, because I'm using the right endpoint, it's going to be f evaluated at, okay, again, for the first one, for the first subinterval, the representative point is x1. For the second subinterval, the representative is x2. For the ith subinterval, the representative is xi. And then delta x is the same. Now remember, I said delta x is the same. It's 1 over n, always, right? And this is xi squared, which is, what's xi? That's 2 over n squared. So basically, you can take out this constant, right? That's 1 over n, and then sum as I goes from 1 to n of this thing here. But as I said, something's wrong here. This is supposed to be I, right? Because xi, x2 is 2 over n, x3 is, that. So xi is I over n. So this I over n squared, right? So that is my Riemann sum based on the right-hand approximation. So this is 1 over n. And then the denominator is n squared. Well, that's constant, okay? So that's still going to be, I can take that outside. And so this just turns out to be I squared after the summation notation. Now, remember, this is basically saying this is 1 over n cubed. And then what are we adding? 1 squared plus 2 squared plus 3 squared plus to the n squared, right? And that's exactly something that we have seen before. Remember in the first section, I gave you that little small lesson on the summation notation or sigma notation. And I said there are 2 important sums that you should know the formulas for. So you don't have to remember those, you don't have to memorize them, but this is one of those things, okay? So if you remember that, there's a formula, which is n minus 1, 2n plus 1, all over 6, okay? So that's what we had. You can cancel one of these n's, makes it into 2. So this becomes 6n squared, and then n plus 1, 2n plus 1. Okay, remember, we're trying to find the approximation for the Riemann sum or the area under this curve, x squared from 0 to 1. Okay, now x squared is a parabola. And from 0 to 1, you have this curve, right? So you really don't expect this area to be a very nice number, or at least you shouldn't. There's no reason to. Okay. All right, so what is that? Well, you could just sort of multiply this out, and what do you get? It's 2n squared, and then you have 2n plus n, that's 3n, and then plus 1 all over 6n squared. Okay. You remember what happens as n goes to infinity? This is second degree polynomial over second degree polynomial in the sense, even though it's n and not x, right? As n approaches infinity, if you want to actually, maybe I should tell you, remember how we did this before? You can divide all of these terms by n squared. If you want to. Okay. And what happens, because that's going to be the same. What happens is these will stay as 2 and 6. This one here is 3 over n. That goes to 0 as n approaches infinity. This thing also goes to 0 as n approaches infinity. So as n approaches infinity, this goes to 2 over 6, which is 1 over 3. Therefore, the integral from 0 to 1 of x squared dx. This is the first real definite integral you are calculating, okay? And we do this in the old-fashioned way. We take the Riemann sum based on our right-hand approximation. We take the limit as n approaches infinity, and you get 1/3. Okay, and this is an incredible answer, because like I said, this is x squared. It's a parabola. It's a curve, not a straight line. You know that a 1 by 1, the whole area of this entire square is 1, and so you can tell this number, the integral, has to be less than half, right? Because half would be the triangle. But to be told that the area under this curve is exactly 1/3, that's kind of surprising. Why could it be? Why can this be such a nice fraction? Okay, but it is, and it's something to remember. Okay. The story I was going to tell you is I have a friend, a dear friend, who teaches at another school in the same state, and he's a veteran professor, much older than I am, and we were just talking about some amazing things in mathematics, and this is one of those things that we both remember very clearly from our undergraduate days. Like, do you remember the time when you first learned that the area under x squared between 0 and 1 is actually exactly 1/3? And it's, oh yeah, that's just an amazing thing. Okay, and this number will not change hundreds and hundreds of years from now. Actually, again, going back to Archimedes, he knew the answer was 1/3. This is like over 2 millennia ago. So this is not exactly a new discovery, but nevertheless, this is a wonderful example to be remembered. All right. I'm going to give you, I wasn't going to do this, but I will give you this less sophisticated example, but perhaps a little more complicated. And this is where the answer is obvious, right? So here, what am I doing here? This is the function y is equal to x. Okay, so the identity function, and we're going to take this, find the area between 0 and 2. Okay, now you know the answer to this question because 2 by 2 is 4, and this is exactly half of that. So the answer is going to be 2. Okay, but the point that what I'm trying to get at is I use the right-hand approximation, and you say, well, if I use the left-hand approximation, you can't expect to get the same answer. And in a sense, this will be very different. Okay, but remember, in the end, you take the limit as n approaches infinity, and when you do that, when you take the limit as n approaches infinity, whatever you see here is going to give you the limit, which is going to be 1/3, even if you used midpoint approximation or the left-hand approximation. Okay, so this time I'm going to use the left-hand approximation, which is going to make things a little more difficult, as you will see. Okay, but nevertheless, I think it's an important thing to remember or to explore. All right, so I have this interval from 0 to 2. I'm going to divide this into n equal subintervals. So delta x is equal to 2 over n, right? It's just 2 minus 0. This entire thing is of length 2. If you divide this into n equal subintervals, the length of each subinterval will be 2 over n. So using the left subinterval, remember, this is x0, this is x1, x2, and so on. What is x1? That's 2 over n. Okay, what's x2? That's twice that, 4 over n, and so on. So xi is going to be 2i over n. Okay, this is important for us to remember. All right, and the xi star. So what is the, so what's the first? This is something we need to know too. What is the first representative point? So remember, the first representative point is the point I'm going to pick as the representation or representative of the first interval. The first interval goes from x0 to x1. And I'm using the left endpoint, so it'll be x0, which is 0. What's the second representative? The representative from the second subinterval. That would be the left endpoint, which is x1. And x1 is 2 over n, 2 times 1. And then what's x3 star, which is x2, the left endpoint of the third subinterval. And that's going to be, x2 is going to be 4 over n, right? So you can see that the nth representative point is going to be xn minus 1, which is 2. It should be the ith representative. It'll be x sub I minus 1, that's 2, I minus 1 over n. All right, so the area can be approximated by, remember, f of xi star times delta x. In this case, we know f of xi, because that would be f of 2 I minus 1 over n, times 2 over n, which is the value of this for each. What is f of value? F of x is equal to, this is the identity function, so f of x is simply x, right? So this is going to be 2 I minus 1 over n. F of x is the same as f of anything is the same as what's in the parentheses. Okay, f of a dragon in this case is the dragon. Okay? F of whatever is whatever. Okay, so this is what we have. Okay, now here the only thing changing is I minus 1, right? So this, you can go ahead and write this as 4n squared. You can factor out everything. And maybe you don't feel comfortable with the summation notation, the sigma notation. That's okay. I took out this, and this. They are all in front. This is I minus 1. So what do we have here? Okay, so that is like saying when I is equal to 1, that's 0. All right, so 0 plus 1 plus 2 plus 3 plus, well, that's that arithmetic sequence we were talking about. And the last number is, when you're plugging n here, it's n minus 1. So it is the first n minus 1 positive integer. Actually, this can be ignored, right, if you want to. So you could also write this as the sum as I goes from 1 to n minus 1 of I. That would be exactly the same thing, right? We had a formula. The first n terms would add up to n plus 1 over n, 2. Okay, that would be the sum of the first n positive integers. So if you go not to n, but n minus 1, this will be n minus 1. Okay, and then what used to be n plus 1 is now n minus 1 plus 1, so that's n, okay, all over 2. That is the Riemann sum representing this approximation, left-hand approximation of the area. Okay, I can cancel a few things. This and this, you can put 2 here, and then n, and one of these n's can cancel. So this is what you get. Okay, so this is 2n over n minus 2 over n, or 2 minus 2 over n, if you like. Okay, you can tell what this is. Right? If as n approaches infinity, this approaches 2. Okay, and if you again had taken the right endpoint approach or the mid endpoint approximation, the midpoint approximation, these expressions will change. But as n approaches infinity, the answer will be 2. Now, of course, that is the answer we were expecting, because we knew from geometry the area of the triangle, which is half of the area of the 2 by 2 square. You knew the answer A has to be equal to 2, and that's what we got. Okay, so it may be time consuming and painstaking to do this. Painstaking. But Again, the good news is starting in the next couple of sections, you will no longer have to do this. In fact, this is the only time when you have to actually calculate the Riemann sum using sigma notation. All right. So what can you say about this? Okay, let me make some concluding remarks. And those remarks will be made in the second part of this video lecture on section 5.2.